recording. Okay. So last time in general physics, right, we learned about all these little wonky things about charges moving around in a conductor, right? One of the things we learned about is this J thing. This is the current density, right? And the picture I want you guys to see when you see current density is that how much current, how much positive charge is moving in my conductor per square area, right? This is current per area, right? That's what the current density is, okay? And then we did a bunch of little gymnastics with some equations, right? And figure out that you can actually calculate what the current density is, and it's actually proportional to the electric field inside that conductor, right? That makes sense? The bigger the electric field, the faster the charge is going to move through that conductor, okay? And the problem is that now you end up with this big complicated thing in front of your equation, right? And as physicists, we like to simplify things, right? Why don't we just make this whole thing the number density, E squared, tau, and M? This is all properties of a particular material. So if you have a piece of, what is this made of anyway? It's probably some sort of tin wire. It's probably iron, right? If you have a particular material, that will have a certain number, electron number density in it, right? And the electron charge is not going to change from conductor to conductor. The mass is not going to change, right? So why don't we just lump all those numbers into one variable called the conductivity, right? All this lumping together, okay? And therefore, it simplifies this equation to something that even I can remember, right? J equals sigma E, right? The current density is just the conductivity, which makes sense, how conductive that material is, times how big of an electric field you apply in order to move those electrons around, okay? But what happens is that we introduce this, we did a little backflip right away, where a lot of times we actually find out it's actually easier to work with this number called resistivity instead. And this is what the next, this last section in this chapter is going to be about. How can we calculate the resistance of a particular conductor, right? If we know the resistivity and then the cross-sectional area, right? And how long that wire is, okay? And we're going to see how this occurs, okay? Any questions on the review before I move on? Okay, everybody is expert in conductivity and resistivity and current density now? Hopefully, maybe. It'll take a while, I mean. Okay, so so now let's keep thinking about what actually happens when you apply, when the current is passing through a conductor, right? So this little gold little column, right, is once again our conductor. Just imagine it's like made of copper or something like that, right? And the idea is that, well, the positive charge, right, I know that is actually the electrons that's moving, right? In our picture of it, theoretically, we're just thinking about positive charge moving in the direction of the electric field, right? Because effectively, that's the same thing as electrons moving opposite, and you don't want to deal with all these sign flips, so that's why we're going to just think about positive charge moving along this wire, okay? So since there's an electric field inside this wire now, right? Because in electrodynamic, there is electric field allowed in the conductor, where if it's static, it's not. What happened is that when you go from point, let's say, on the left-hand side of this conductor to the right-hand side of this conductor, right? You're following an electric field, right? And remember that the change in voltage across an electric field is actually this complicated E dot ds thing, right? But right, let's say if we can assume that the electric field is constant inside that that conductor, right? This is actually can allow us to bring out this electric field, right? And therefore this just turns into E dot delta S. In this case, if we just make it along the x direction, right? This is just going to be negative E times delta x, right? However long this is, and the length of this is L, right? Right? So the potential, meaning the voltage of these charges that are here, drops from, whatever the initial potential is, it drops to some other potential. And the way we quantify that is just that it's a drop, therefore it's negative, right? It's E times L. Okay? All right. So let's just save that in our head for a little bit. Okay? So when you have a macroscopic amount of current passing through this material, okay, meaning macroscopic as opposed to thinking about, little electrons, right? We're thinking about 10 to the 20 electrons all passing through, right? Okay? So this quantity, right, is quantified by our definition of current, big I, right? And that's just the current density times the area. That's just a definition, right? Because we define current density to be that. So if we solve that for current, we just get Ij, right? Okay. So Ij, right? We have an equation for the J part up top, right? J is just sigma times the electric field, right? So what we can do is we can replace the J part with sigma times E. Okay. In fact, once again, we're going to do a little backflip, right? Remember that conductivity is just the inverse of resistivity, which unfortunately has this, weird Greek letter rho, right? Which I always have trouble writing. Okay. So the current is actually going to be equal to the electric field, proportional to the electric field. The bigger the conductor, the more bigger the cross-sectional area, the more current you get. Hopefully that makes sense. If you have a bigger pipe, right, more water can flow through. And it's also inversely proportional to the, what's I going to say? Resistivity. Okay. So instead of, remember this E here, right? This E here, right? We actually figured out what E was previously. Well, E is just the change in voltage across that conductor divided by the length of that conductor, right? So what we're going to do is actually plug this in for E, do a little bit of, algebra gymnastics. So now that we found out that the current is actually equal to, replacing this E with delta V, right? But we get an extra factor of rho times L on the denominator there. Okay. Once again, we have a complicated, equation that has more than 3 variables. What I'm going to do is we're going to lump all of this stuff together, okay? And we're going to call that resistance as opposed to resistivity. So be really careful about the slight difference between the wording. Resistivity is how resistive that one particular material is, right? Without thinking about the dimension, how thick it is, how long it is. Resistance is for a particular size, okay? So if a material is made of copper, right, that instantly tells you what the resistivity is. But if I also tell you the dimension, the cross-sectional area, and the length, all those 3 things combined together allows me to calculate the resistance, okay? So it's a property not only of the material, but also the dimensions of it, right? The physical dimensions of it, okay? So resistance, what I'm going to do is we're going to stick this in here, right? We're going to make this whole thing 1 over R, which is the symbol for resistance, okay? So therefore, resistance is actually the resistivity multiplied by the length of your conductor, okay? Let me go back to this cable multiple times, okay? Right. So this particular cable is made of, let's just say it's copper, okay? It's probably not. It's some sort of alloy, okay? So by knowing it's made of copper, I instantly know what the resistivity is, okay? But knowing the resistivity, the length, and how thick the cable is, basically the cross-section area, I can calculate the resistance of it, okay? And once I have the resistance, I can replace this thing with 1 over R, and therefore basically come up with this idea known as Ohm's law, okay? Where I don't actually like the way that the book writes it. It's easier to remember. It's just delta V equals to I times R, okay? Some of you guys may have seen this before, right? V equals IR, okay? Be a little careful, okay? With this little delta V thing indicates if I have, let's say, a current, let's draw that on the side, right? Some current I passing through here, right? The voltage here, V plus, voltage here, V minus. This delta V indicates V plus minus V minus. How much did the voltage change, aka how much did it drop going from the left end of the resistor to the other end of the resistor? Okay. Okay. And resistance, and this is where the definition of ohm came in from last time. I told you not to worry about it until now. Now we actually can define what an ohm is. Okay. The resistance, right? If we actually solve Ohm's law for R, right? R is just going to be equal to delta V over I, right? Delta V, of course, will have units of volt. I will have units of ampere, okay? And we're just going to define that, well, all of that, a volt per amp is actually what's known as an ohm after some guy named Ohm, okay? And we're going to use the Greek letter omega to indicate that. So that's the Greek letter capital omega, okay? Just this weird symbol like this, okay? All right, so, and resistors come in different sizes and shapes. I'm just going to show you guys a couple of them. Let's see. This is where we're going to switch to dock camp. Let's see if the dock camp works. Dock camp, dock camp. Okay, so I'm going to show you guys the multimeter that we're measuring this stuff with. Right, let's have this upright. Okay, so for example, right, if I have just this wire, let's switch to resistance mode. Right, I'm just showing you a wire. Right, if I connect both ends of this wire, I will get some resistance. Okay, this is actually quite large. Why is this so big? This is messing with me. Let's connect it like this. Let's connect it like this. Okay, you guys see that number? It's like, it's moving around because I'm not holding it completely still, like 0.4 ohm. Okay, so in reality, right, even a conductor, right, has some resistance to it because it's not made of a superconductor, right? So that's one demonstration. So like a meter long wire will have a fraction of an ohm in resistance. Okay, that's just to give you guys some numbers. Okay, what I can do is connect to, look at this thing. This is a resistor that you probably see. Oh, I'll show you guys in the back in the lecture note, right? If you measure this one, and hold it still, right? It's like 540. Okay, so this is a typical resistor. There's some color coding on it. I don't know if the lab teacher is going to force you to memorize what these colors means, but basically you can figure out what the resistance is by just reading this color. Okay, so that's a resistor. This is actually made of ceramic, so it's a less conductive material. That's why you can make the resistance higher. Okay, another type of resistor. These are actually called potentiometers. I call them a variable resistor. So if I connect this, now I need 3 hands. Okay. Okay. All right. And connect it to this. I can use 2 hands to get this in there. Okay. You can actually, so right now it's at 200-ish, right? You can actually, I'm turning this little knob here to increase and decrease it. Okay. This is known as a variable resistor. The way this works is, where's my pen? Right, is that you basically have a long resistor, right? And there's a little wire that's actually adjustable that you can move up and down, right? And then if you connect this side, right, to this, to your ohm meter, right, by making this taller and shorter, you can actually change the resistance, because resistance is not futile. It's actually rho times L divided by A, right? So the longer the resistor, the more resistance you get, okay? And we're going to see this geometrically. Okay. Go turn this off, laptop. And now I lost my pen. There it is. Okay. So these are different, types of resistors. So that's the variable one. These are the ceramic resistors I told you about. This one is actually kind of neat. It's actually what's known as a photoresistor, meaning that if you expose it to light, it gets lower resistance. If you don't expose it to light, it increases the resistance. So it's like a light sensor. Okay. And as I show you, so on the little demo, right? There are ways to measure resistance, and we already did a little thing with capacitors. And there are these devices that the book describes in this section for some reason that also measures current. And whenever you see a device that measures current, the unit is in amperes. That's why this A is here, right? If it measures voltage, right, then it has a big V here. So a lot of times when you see these devices, it doesn't say, oh, this little knob, measures voltage, but it just tells you it's V. And they assume you know that V stands for voltage, and therefore it measures voltage, okay? All right. We'll discuss these little devices that measures these things when we learn about magnetic field afterward, okay? Anyway, so let's talk about our little current situation, right? So instead of connecting your battery now to capacitor, now we're going to connect it to this little resistor. So if we connect a battery with some EMF, electromotive force, which is a voltage, not a force, right, with some EMF of E, right, and we connect it to some resistor, what happened is that on a wire, okay, inside the wire, what we're going to do in this class is just assume that the voltage drop along that wire is minuscule, right? We saw that it was like 0.4 ohm, right? And where a regular resistor is like 500 to like 5,000, right? So compared to the resistance of the resistor itself, right? The wire, it doesn't give you that much of a voltage drop. Okay, so we can just assume that, right? Whatever, if we declare this point to be 0, right? This will be EMF. We can just assume that, right? We're going to model it as if there's no voltage drop when you're moving along a wire. Okay, so that's an important point. Okay, but when you go across this resistor, the voltage is going to drop from whatever EMF is, right, all the way down, right? When it exits on the other end, right, what happened is that, well, it's going to be the same voltage as here because we're assuming along the wire we don't have any voltage drop, right? So this 0 actually goes all the way out here, right? So that's what this little diagram down here is supposed to show you, okay? Where along, this is on the wire, right? But when you're traveling across a resistor, the voltage is going to drop linearly, okay, until you get to the wire again where it's constant again, okay? So this is E and this is 0, okay? So therefore, right, the voltage drop in this particular system, right, is just whatever the EMF is times the current across it. So we can, massage this equation to calculate what the current is. The current is just going to be the voltage drop, which is, right, the EMF divided by R, okay? And now I'm just kind of rederiving Ohm's law and just playing around with it, okay? But Ohm's law is one of the most useful ones, right, where the voltage drop across the resistor is just the current times the resistance, okay? But just be careful of the sign, okay? It's always going to be on the high to the low. That's the drop, okay? Okay. There are other devices. Oh, so before I move on, these devices up here, right? These are called ohmic devices, okay? Because they obey Ohm's law. They obey Ohm's law, okay? Where delta V equals to IR, right? There are other devices that does not do that. A prime example of this is known as a diode. Okay, diode, they look like these little orange little bob thing. The weird thing about diode is that instead of being ohmic, meaning the more, so the equation we have up here, the ohm equation, right? I equals EMF over R, right? Notice that since the R is a constant, right? The bigger your EMF, the bigger the battery you connect to it, the bigger the current, right? And they're proportional to each other. Okay? So in an ohmic material, what's going to happen is that if you plot current versus the voltage you apply to it, right? You're going to get it more and more and more and more current, right, as you increase the voltage, right? And the slope of that is actually 1 over R, right? Because the slope of this function is 1 over R. Okay? For a diode, it's actually a semiconductor, okay? Whereas it does this funny thing where as you increase the voltage, nothing happens, the current stays at 0, but then all of a sudden, it'll actually turn on basically exponentially, okay? And this is a semiconductor material, and in case you're interested in learning more about this stuff, there's the next version of this class, which is called Physics 4250, that's offered in the fall semester, okay? And it's just the analog and digital electronics, okay? All right. So let's stop to think. So how are these devices useful? So one application of this is actually these percentage fat measurement devices, which is not extremely accurate. And the idea is that if you just have a person holding a resistance meter, okay? I'm not going to do the doc cam, but here, Anthony, do you mind holding this so this class can see it, right? Humans have some resistance to it. What's my number? 330. 330, okay? 330 ohms, right? Okay, yeah. Ohms or mega ohms? Kilo ohms, okay. Yeah, 300,000 ohms, okay? So that's because what's happening is that when I touch these two things, okay, you don't have to hold it up, right? Current is going from this device into my hand through my body out on the other side, so I have some resistance, right, to electricity, okay? And I think is fatty tissues have less resistance than muscles. And therefore, no, actually it's the other way. Muscles have less resistance compared to fatty tissues. So by measuring someone's resistance, you can actually figure out what fraction of their body is made of fat. That's one thing that I didn't know. I mean, I had these devices since I was growing up, but then never knew how they actually work, okay? And here's a little diagram and a little challenge example that we're not going to have time to go through today. But the idea is that different tissues in your body will have different resistivity, so therefore when you actually measure it, you will have get a different thing. But before you jump into the worksheet, I just want you guys to maybe get through this idea real quick before everyone jump into the worksheet. So let's say if I apply a 1 volt potential between my two hands, right? The same thing what I just did in front of Anthony. And if we measure the current of 1 milliamp, okay, what's the total resistance of my arm, okay? So is there a way for us to figure that out from what we learned? Is it 1 ohm, 10 ohm, 100, 1,000, or 10,000? Purposely made the math easier, and milli is 10 to the minus 3, okay? How many think it's 1 ohm? If we, what about B, 10 ohms? C, 100? 100? One think it's 100, okay? What about D? How many think it's 1,000, okay? How many think it's 10,000? Okay, so we can actually figure what this is, okay? And I'm not gonna, right? Remember Ohm's law, the way you wanna remember it is just that, well, the change in voltage across some resistors, in this case my arms, okay? is the current times the resistance. So if you solve this equation for R, right, it's just a change in voltage divided by the current. The change in voltage here is 1 volt, right? And the current is 10 to the minus 3 amp, right? If you do that multiplication, you get 1,000. And a volt per meter is an ohm, okay? So therefore, you actually get a D as the answer. Okay, so that's the end of the chapter. And then